everyone, welcome to this manufacturing process technology part 2 module 7. We were looking into the subtractive techniques, looked into the polymer MEMS and to some extent into three-dimensional structures, and now we are again going back into directional etching or anisotropic etching. So as we already told that the subtractive processes of etching are basically about some etchant solutions which come in interaction with surfaces, and it creates some kind of a impression or an engraving on the top of that particular surface. So this engraving either can be created in an isotropic manner, as you saw earlier, where there is an equal influence of the etchant along the the surface atoms in all different directions, and there is a rate along the vertical as well as the horizontal direction formulated in that manner. Today we will look into this anisotropic wet etching process, which is a very specific process in the silicon industry, and it is also known as the hydroxide etch process, and basically it is a redox chemistry between several states of silicon, where because of the hydroxyl ion furnished by the etchant solution, the silicon gets converted into SiOH2 plus. This is actually a dissolvable state in the solution, and so the silicon atom is basically converted into something which dissolves in the solution in this particular manner. So there is effectively a 4 electron transfer process which is involved whenever we are talking about hydroxides to etch silicon, okay. And this 4 electron transfer process is actually also dependent on the plane which is being etched, or the particular plane of silicon which is being etched. For example, let us say if we talk about different planes of silicon, let us say there is a plane along 100 direction or 110 direction or 111 direction. We already know what these planes are because I had defined this earlier at some point of time. Now if I look at the 100 plane, which is actually perpendicular to the 100 direction. So let us say there is a orthogonal system, and this is the 100 direction, and the plane is perpendicular to the 100 direction, okay. So this plane would typically have a neighborhood of atoms which may be different than one which concerns the 111 direction. So this, for example, is the 111 direction, and this neighborhood would be completely different than this neighborhood. So it so happens that the number of atoms in the neighborhood of the etched portion is very critical to determine what is the bindability of the electrons to the silicon atom. So if supposing there is a case where the bindability to the silicon atom of the electrons are lesser because of a proximity or a neighborhood which is more amenable to creating less binding energies. So in that case the electron can be easily furnished, vis-a-vis a case where the environment of an atom releasing the electron would have more binding to the electron, would be furnishing the electron at a very slow rate. So the 111 plane has a stronger binding force to the electron and makes it more difficult to release the electron, okay. So therefore, as we are talking about a 4 electron transfer process which would execute this dissolved state SiOH2 plus from silicon in the anisotropic etch, the plane 100 which have lesser binding of the electron would be able to furnish more number of atoms, and the rate of reaction would be more in comparison to 111. So 111 in fact is the slowest etch step in the whole process of this 4 electrons getting furnished, and so therefore when we start the etching process on a silicon wafer, whatever directions it meets, the slowest etch would be the direction 111, okay. So this results in some kind of a a structure which would typically mean the eventual shape or the structure which would emerge out of any 100 or 110 would be the 111 direction, okay. So this is the slowest step. So in fact if two such planes meet together, then the etching would be negligible or it will stop completely, and so this is something that has to be avoided in the anisotropic etching, that the two 111 planes which are getting formulated in the wafer should not meet each other, okay. So because being the slowest etch step, it is important that this, so obviously the alignment of the etching process would be such that they will all merge to this 1 direction, and that creates some kind of a anisotropicity or directionality in the etching, okay, process. So the following are more or less used for the hydroxide, for furnishing the hydroxide groups. So there are these alkali hydroxide etchants including potassium hydroxide, sodium hydroxide, cesium hydroxide, rubidium hydroxide, lithium hydroxide, so on and so forth. There are very good ammonium hydroxide etchants. For example, this TIMA or tetramethyl ammonium hydroxide is a great etchant to perform anisotropic etching. You have CH3,4NOH as the structure, or ammonium hydroxide NH4OH also is a reasonably good etchant which provides such or furnishes such hydroxyl groups for the electron transfer to take place. You have again ethylenediamine pyrocatechol, a mixture of ethylenediamine, pyrocatechol and water. This is a hazardous process, it causes cancer, so industry does not accept this process very highly, although whenever it is done it has to be used using a lot of safety measures to handle the fluid particularly. The other etchants in this area are hydrogen water combination or amine gallate etchants, which are normally used for furnishing the hydroxyl groups needed for providing the anisotropic etch step. So let us actually look at how this this overall 1 direction formulates an angle with respect to the conventional 001 or 010 or 100 or let us say 111 direction, so 110 direction. So in this particular example we are talking about etching a microchannel in a 100 principal direction wafer with a hydroxide etch, and we want to determine the angle between the 111 plane and the 100 plane, which is actually a very simple issue. It is about how this direction would be in comparison to this direction here. The 111 plane is in this direction, as you know, it is this is the 111 direction and plane is perpendicular to it, and the plane which is 100 is actually perpendicular to 100. So it is about a dot product of these two vectors together, which would give you an idea of what is the angle, effective angle which would get formulated with respect to the principal 100 direction, which is the growth direction of the crystal in this particular case, okay. And the other issue that we would like to find out is something about the etch rate. So if the top channel width and etch rates are given, let us say the top channel width is about 100 microns and the etch rate is about a micron per minute, what is going to be the bottom channel width after 20 minutes of etching, and how long it will take until the etching process kind of stops. So in order to do this numerically, based on the crystal structure, the angle between the fast etching plane (100) and the slow etching plane 111 is the angle ABC, this being A, this being B, this being C right here, okay. So this is equal to alpha, and if I look closely in triangle DAE, this half of the triangle, the angle DAE is obviously 90 degrees, it is perpendicular about the point A, and the height, if we assume these two to be unit vectors, the height AB is actually equal to root 2 by 2, okay, because obviously this is also perpendicular AB is actually perpendicular to DE, and if I had root 2 by 2 and root 2 by 2 here, the summation of that would actually result in 1, okay, which is actually the hypotenuse for the triangle DAB. Okay, so that's why AB is root 2 by 2. So in triangle ABC with angle BAC equal to 90 degrees, as you can see here, and AC equal to 1, the angle ABC will be given by alpha obviously equals the tan inverse arctan of AC by AB. Okay. So obviously in this triangle ABC, alpha is nothing but the AC which is one of the sides divided by AB tan inverse. Okay. So geometrically this comes out to be equal to arctan of 1 divided by root 2 by 2, which is 54.74 degrees. So this angle alpha here, which formulates between the 100 and the 111 direction, is actually 54.74, and that's what happens normally in anisotropic etching. So let's now consider the etch rates and the total etch window size which is concerned. So let's say after 20 minutes, as given in the problem statement, that what would happen to the bottom channel width after 20 minutes. So after 20 minutes, the corresponding to an etching rate of 1 micron per minute, the channel depth that will be obtained is around 20 microns, okay, 20 times 1 micron per minute. So that is going to be the D value here, 20 microns, and the etching is happening anisotropically, and the walls are getting formulated because of that. The problem statement says that the vertical etching rate is 1 micron per minute. So if we assume that to happen, obviously with the D value and the angle value here in this particular triangle, I should be able to get what is going to be the WB. Okay, WB is the value corresponding to the bottom channel width. So the bottom channel width thus is given by Wt minus twice d by tan alpha, okay, as can be visible here. D by tan alpha is this particular value right about here. So twice this taken off from Wt, which is the total top channel width, would give the bottom channel width. So this comes out to be equal to Wt minus root 2 d, because obviously tan alpha is equal to root 2, okay, in this particular case. And if I substitute the value of Wt as 100 microns minus root 2 times of 20 microns, which is the etch depth formulated by the etching rate at 20 minutes. So this comes out to be equal to 71.7 microns. So that's how WB would be, about 72 microns, the lowest or the lower channel, the bottom channel width. And supposing as recorded in the second part, that how long will the etching process stop. So as you already know that the stopping of the process would happen if all these 111 planes meet together. In other words, WB goes to 0, okay. So that is where the etch typically would stop. And so in order to calculate that, we put this Wt minus twice d by tan alpha, which is equal to WB, equals 0, So the D max or maximum depth would be equal to Wt by 2 times of tan of alpha, or in other words Wt being 100 microns, this is 2 by tan alpha is actually root 2. So this comes out to be 70.71 microns. So in fact going up to 70.71 microns would correspond to achieving a maximum D max where both the 111 planes will meet and the etching will stop. So the time until such an etch stop would then be equal to D max by 1 micron per minute and this would be again 70.71 minutes. So much time is needed for the etch to stop when both the 111 planes typically meet each other, as in this particular case. So let us now go to another very important area of the microstructuring or microfabrication, and particularly very well needed in the case of biomedical devices or biomicro devices, which is about how to bond the various wafers together so that the cover slip or the cover can be bonded to the base, or for example when we are talking about a polymeric device, the polymer structure can be bonded to a hard platform to make a hybrid bio device or hybrid device which can be used for biomedical diagnostics. Okay. So here let us talk about now different strategies which have been thrown in the literature for different wafer level bonding schemes. So the first strategy which comes to mind for such bonding is also known as field assisted bonding, which is also known by the name of anodic bonding. Okay. And what such bonding typically does is that we take in such a bonding a silicon material. Okay. Let us say this is a sort of a silicon material, and make this the anode. Okay. And then there is a glass material which is typically soda lime glass, which is made the cathode. So obviously the soda lime glass would contain a lot of Na plus, and the silicon, by virtue of its oxide, native oxide, will have a lot of O minus. So if silicon is made the anode and the glass is made the cathode, there would be a migration of the soda lime and the oxygen vacancies or O minus moieties to opposite electrodes. So the sodium would go towards the cathode and the O minus would go towards the anode, and there would be actually creation of something called a depletion region. Okay. So in this particular case in anodic bonding, what is happening is that because of the migration of the positive and the negative ions to the opposite electrodes, there is going to be a depletion region, and if such a depletion region happens where there is no field which can otherwise be recorded on an instrumentation, if there is a small let us say nanometer or even let us say a very small current measurement device which would actually pick up the current and see when it drops down. So if the depletion region formulates, the current would typically drop down. Okay. So that point the silicon and the glass is heated up because of the anode. So you heat it up to a temperature where there is fusion bonding, okay, which happens between the glass and silicon, but in the absence of the field. Okay. So that becomes a very permanent a bonding which is permanent or irreversible in nature, and it results in thin cover slips getting permanently bonded to, let us say, silicon substrates which are highly structured, or they have printed electronics on the silicon, and you can create various features or structures at the mem scale, okay, or the micron scale using such methodologies. So you are doing the enhancement of ion mobility from the surfaces, results in the creation of a strong field, and the bonding happens by fusion, between the substrates. So there is another way of doing bonding, which is the easiest way of doing it, which is with an intermediate layer. So we are talking about now an adhesive. So there is an adhesive which is put between the two substrates that you want to bond. but there is a disadvantage with this method, that because there are going to be substructures in both the substrates, there is a possibility of the adhesive to get into such structures and spoil the whole essence of MEMS fabrication. So, but there exists such a way of using an intermediate adhesive layer to bond different layers. Obviously, then you will have to be very selective on applying the adhesive. You cannot apply it to the structures per se, but then surrounding areas of the structures, but it requires costly instrumentation to work at that resolution to even spray or discharge the adhesive. There is a means of doing direct bonding, where two substances either are, or two substrates are either bonded to each other by thermal means. For example, if we just remove the field here and just apply higher temperature, there will be a fusion bonding between the two surfaces. But again, because the thermal processes are really not preferred to that extent, because of the fact that there are thermal stresses which are induced, and can be a warping or a change in the characteristics of the wafer, and there may not be good bondability between them because of that. And so typically we try to avoid creating such kind of defects into the structure which we are working in, and therefore thermal bonding is not very preferred means when we talk about microstructuring alone. Then there are these means which are available particularly in low surface energy materials like polymers, which can be bonded to each other or to some glass or silicon substrates by means of exposing to oxygen plasma, which quickly changes the surface energy of such structures. So, such kind of bonding schemes are very widely available, particularly when we talk about polymer MEMS fabrication. And what is really plasma? Let us delve into that a little bit and try to look into from a perspective of how they can create plasma, or what really is plasma, or what is the kind of effect on the anode which would happen because of such plasma exposure. And in fact, this knowledge that we will be sharing would be useful for you to understand not only bonding between substrates, but also things like dry etching, for example, where there is a plasma state of gas created. Remember, I told about physical chemical etching or physico-chemical etching, where there is a deep reactive ion etching of various means possible by creating a plasma and a driven diffusion of the plasma into the substrate by using a bias voltage. Okay, so all these different applications of MEMS would sort of include this oxygen plasma based fabrication. So let us look into the theory of plasmas a little bit. So as we all know, plasma is a system of overall electrical neutrality comprising of positive and negative charge carriers. So obviously there is a shift in the overall charge center. The positive charges are separate in forms of ions, and then there are electrons which are all going around in a gaseous state. And if you look at plasma categories, you can either have plasma in gases, so gas plasmas. In liquid, for example, salt solutions are very good examples of plasmas. Even our blood plasma is a sort of plasma. There is a lot of positive and negative ions within our the plasma part of our blood. And then there are solid plasmas, which are in terms of fixed ions and moving electrons. The whole semiconductor area is comprised of solid plasmas. And if we talk about gas plasmas, again we can categorize them into two different types. One which is formulated because of thermionic effects. Typically you heat the temperature of the gas to a level where electrons start coming out, and the electron temperatures are sort of comparable to the surrounding gas temperature. So they're very hard to obtain because obviously the level of temperatures that we are talking about are a few thousand degrees Kelvin, so a few thousand kelvins, which is not possible on a lab scale. However, we can with other ways and means increase the electron temperature to be exceeding the surrounding gas temperature, and to an extent that the kinetic energy of the electron forces it out of the orbital of the atom, making the ion and electron come into existence. So such plasmas are known as cold plasmas or laboratory plasmas, and this would be our focus study because we are interested more into this area. So how do we really increase or enhance the electron temperature is of a big question, and there are many means to do that. One of them is called DC glow discharge, then there is an RF discharge, there is a magnetically enhanced plasma, and these are the three most basic forms of plasmas which are very widely used. I am going to cover one by one these with some animations or some schematics which would talk about the basics about these plasma systems. So let us first look into the DC glow discharge. So there is a chamber here, for example, and they have two plates like a capacitor, and there is a biomolecular gas which is introduced into this chamber. So before introducing it, there is a vacuum pump which sucks the chamber to almost the level of about 10 to the power of -3 torr, or about a millitorr level, and then there is a gas inflow of this biomolecular gas XY into this chamber, and then the gas is flowed at a rate where the inflow outflow makes a certain pressure come as an equilibrium state of this particular chamber. So in this kind of a, let us say we have 1000 millitorrs or about 1200 millitorrs, in that particular level it is considered to be very high pressure, okay, in such a system. So you are existing, you are sort of creating a situation where there is a high purity only biomolecular gas present and nothing else in this particular chamber. So you have a high voltage source coupled to one of the electrodes, and you suddenly switch on this high voltage source. So there is a surge voltage being applied here to the one of the plates, and what happens because of that is that there is a situation where the gases which are adjoint to this plate, their breakdown field is exceeded and the electron comes off. So when the electron comes off into the gas with a certain energy, there are many happenings which would happen within such a chamber. One of the processes are called dissociation. When this high energy electron, you can see this hash here means energy, is associating itself with a bimolecular gas molecule otherwise present within the chamber and converting it into free radicals. So you have the X and Y free radicals, and the electron does not have any energy anymore. Or there is a possibility that another such high energy electron can create atomic ionization by going to strike a free radical or a free atom and then converting that into an ionic state and creating another electron. There is also a possibility of molecular level ionization where the whole molecule as such is inducted with a positive charge and an electron is emanated out of the molecule. There can be an atomic excitation state, and this is something very interesting, that this results in most of the glow of the plasma processes. So this is a state where, let us say, an atom which is having an electron in a certain orbital, let us say this is the nucleus and there is an electron here in one of the ground states S1, goes suddenly to a higher state S2 and stays there for a while before coming back, okay. So you are not essentially taking this electron out of the bounds of the atom and limiting them within a state transition merely from a higher from a lower state to a higher state or an excited state. So this the atom X is now having an excited state electron, and there is a possibility that within a very short time this electron will come back, and once it comes back it sends out a radiation H nu, okay. So similar thing can happen for molecular excitation, and in fact we can say that these are moderate energy electrons which would cause such transition, because if the energy was high then the electron would have really gone out, and this is not happening, so it is quite low. So the chamber is evacuated, the switch S is closed, the DC source is protected from high voltage by the inductor. You can see there is a DC source which will be, I'll talk about later why a bias is needed, this is for sustenance of the plasma. So and then you are creating the following events in this particular chamber because of the electron discharge, okay. So the high voltage generates electric field equal to the breakdown field of the gas, and this makes the gas conducting, and an arc is flashed. So there is an arc here. Now what you are doing is that once the voltage has been applied, it is switched off, and there is an arc generated which has electrons and these different species which are there in the medium, and we are applying a bias voltage. So the bias voltage is being applied by this secondary source here, and what would happen is that it will make one of the electrodes negatively charged. Let us say this is the cathode, this is the anode, and typically all the ions which are formulated here would go towards the cathode, and the electrons would travel towards the anode. So, I will just sort of continue this in the next lecture, and in the interest of time sort of close this module, but in the next lecture we will see that how it is important for this translation of the ions and electrons to keep the plasma going on, or to sort of self sustain the plasma with time, and the energy of the energy source, the DC energy source, is mainly responsible for that self sustenance. So, with this I would like to close this particular module. See you in the next module. Thank you.